In this video, we will discuss energy band structure. So we now know that energy band of a semiconductor is composed of two bands and one forbidden band gap that separates the two. The energy band above the forbidden band gap is called the conduction band, and the energy band that is below the forbidden band is called the valence band. And conduction band and the valence band represents the ranges of energy that electrons are allowed to have, whereas the forbidden band gap is the region of energy where electrons are forbidden. Now, in this diagram here, you can see obviously that the y-axis in this diagram here is the energy axis. So going up is the higher energy and going down is the lower energy for electrons. Now, then the question is, what is the x-axis? Well, the x-axis implicitly is the position, the real space. And this is a useful diagram, and we will be using this commonly throughout the course. Now, there is an alternative representation of energy band structure that uses a different axis. And that's what we will introduce in this video. So, in quantum mechanics, electronic states are given as a solution to Schrödinger's equation. And the standard Schrödinger's equation is shown here in this equation. So the first term here represents the kinetic energy, and the second term here is the potential energy, and E here is the total energy of the electron, and psi is the wave function of an electron. Now, if you are dealing with an electron inside a solid, inside the crystalline solid, then because the crystal structure has a periodicity, the potential energy, electrostatic potential energy produced by these individual atoms will also be periodic. And the key theorem in the quantum theory of solid is a Bloch Theorem, who states that the solutions to this type of Schrödinger's equation is given in the form as shown here. That is, a product of an exponential function with another function which has the same periodicity as your potential or the crystal structure. Now, if you're familiar with optics or electromagnetics, then you can think of this as a plane wave. This exponential term here in this solution is simply a sine and cosine function. It's a plane wave, and it has an amplitude which is given by this u function, periodic function. So it's a periodically modulated plane wave. If you're not familiar with optics and electromagnetics, that's okay. This is just a sine and cosine function with an envelope function which modulates its amplitude with a certain periodicity. Now, the key point here is that we have introduced a new variable, k. So, because your wave function and energy contain k, we can use this k vector in general, because we're dealing with a 2D or 3D space. This k vector is used to specify wave function or energy. Okay. And this k is called the crystal momentum, and it is a good quantum number with which we can specify electronic state. So now the next question is, what is k really? K, if you are familiar with Fourier transform, it's simply a Fourier conjugate of a real space variable. Okay, so the k space is a Fourier transformed space of a real space. In physics, this space is typically called momentum space. In the case of crystal, because the real space is periodic according to the Bravais lattice, the Fourier transform space should also be periodic, and the lattice that defines the periodicity of your Fourier transform space is called the reciprocal lattice. Now, reciprocal lattice is also Bravais lattice, so it is periodic. So you can define a unit vector and also unit cell, just as we did with a real space lattice. The unit cell, the smallest unit that repeats in the Bravais lattice, in the reciprocal Bravais lattice, that is called the first Brillouin zone. And because the reciprocal lattice is periodic, everything should repeat according to the periodicity. And what that means is that when you're dealing with energy levels as a function of k, you only need to consider one unit cell because everything else should just repeat. So when typically specifying energy as a function of k, we only consider the unit cell, which is the first Brillouin zone. Now, most semiconductors have either diamond crystal structure or zinc blende crystal structure, both of which belongs to face-centered cubic Bravais lattice, or FCC Bravais lattice. So the reciprocal lattice of these crystals would have the reciprocal lattice of FCC crystal structure, which is body-centered cubic structure. That is, if you Fourier transform FCC lattice, then you would get BCC, body-centered cubic lattice. And therefore, the first Brillouin zone for these crystals will be the unit cell of a body-centered cubic lattice. And the unit cell of a body-centered cubic lattice is shown in this diagram here, and it is a truncated octahedron. Now, there's some notation convention that we need to know to read these energy band diagram. Here is the unit cell of the BCC crystal. So this is the first Brillouin zone of the FCC based crystals like diamond and zinc blende crystals. The center of the Brillouin zone here, which corresponds to k equals 0, is called the gamma point. The Brillouin zone boundary along 1, 0, 0 direction is called the x point. The Brillouin zone boundary along the 1, 1, 1 direction is called the L point. And these are the representative high symmetry points. And this diagram also shows some lower symmetry points like k, x, and u. K, for example, is the Brillouin zone boundary along 1, 1, 0 direction. Now, with this notation convention, we can read an energy band structure or energy band diagram which plots energy as a function of k vectors. So in this diagram here, this is a silicon energy band structure. The y-axis is energy, of course. X-axis here is various k values inside the first Brillouin zone. And you can see there's a gamma point here. That's k equals 0. And you can see L point here, which is the Brillouin zone boundary along the 1, 1, 1 direction. X point here is the Brillouin zone boundary along 1, 0, 0 direction. So these various lines represents the energy corresponding to that particular k vectors. And you can see here that there is a region where there are no allowed energy levels. So that will be basically the region shown here. And this is the forbidden band gap. And all of these lines sitting above the forbidden band gap belongs to the conduction band. All of these lines below the forbidden band gap corresponds to the valence band. Now you have two alternative energy band diagrams. One is this sometimes called the spaghetti diagram. Looks very complex. This is the energy band structure specified or plotted in k-space. The very first energy band diagram that I've shown at the very beginning, which is simply represented as horizontal lines, conduction band here, valence band there, forbidden band gap in the middle, is a band diagram depicted in the real space for a homogeneous semiconductor, that is. That's why the band diagram is simple horizontal lines. If you have a heterogeneous structure, then these horizontal lines may curve, bend, and we will see those examples later in this course.